Right. So again, we're diving into some serious physics today.
Oh, yeah.
We're talking about CSpace, and
Okay.
it's this model of reality where everything, and I mean everything, is like a single continuous material.
Huh.
Like, imagine cosmic Play-Doh, but like way more complex.
Interesting.
And the sources you shared go deep into this search for a specific structure within CSpace.
Oh, okay.
It's called a resonance carrier ball, or they call it an RCB. The big question is, can this RCB finally explain how fermions exist?
Right.
You know, those particles like electrons that always seem to break the rules?
Yeah, what's fascinating is that this model isn't just trying to explain like one little piece of the puzzle.
Yeah.
It's aiming for the whole picture, a complete machinery of reality.
Whoa.
I'm talking gravity particle behavior, the works, like all arising from this one fundamental substance.
So, okay, let's break this down.
Okay.
So CSpace is this continuous 3D material, right?
Uh-huh.
But the researchers are simulating it on a computer, which means they're working with a discrete 4D representation.
Right.
Is that kind of like trying to understand the ocean by looking at like a digital model?
Okay.
Like accurate, but not the real thing.
Yeah, that's a good analogy.
Yeah.
It highlights the limitations that they're working with.
Right.
But the hope is that by simulating CSpace, they can actually see if this RCB structure actually forms.
Okay.
And more importantly, if it can behave like a fermion.
Uh-huh.
Because standard CSpace, as the source points out, can't handle fermions on its own.
Now, I remember enough physics to know that fermions are kind of a big deal.
Yeah.
But remind me what makes them so difficult to model in the first place.
Well, it all comes down to the Pauli exclusion principle.
Right.
Which basically says two fermions can't occupy the same quantum state.
Okay.
It's like a cosmic game of musical chairs, where every fermion needs its own unique seat. And this principle is crucial for atom stability of matter, the whole shebang.
Yeah.
But figuring out a mechanism within CSpace that can enforce this behavior has been a major challenge.
Yeah, and that's where this RCB comes in. So the source describes it as a vortex-like structure that can support resonances.
Yeah.
Are we talking like vibrations within the fabric of CSpace itself?
You got it.
Okay.
Imagine an elastic sheet like a trampoline.
Okay.
Now picture a localized vortex within that sheet, a stable swirling pattern. The source proposes that this vortex, the RCB, can have specific vibrations or resonances happening within it.
So if I'm following correctly, the RCB itself isn't a fermion.
Right.
But the combination of this vortex structure and the specific way it vibrates is what might give rise to fermionic behavior.
Exactly. It's like the RCB sets the stage, and the resonances are the actors playing the role of a fermion.
Oh.
This idea of emergent properties, complexity arising from simpler components, that's key here.
But here's where it gets really trippy.
Okay.
The source mentions that the RCB mimics the topology of a ball.
Yeah.
Which apparently can't actually exist perfectly within CSpace as it's currently defined.
Right.
It's like fitting a square peg in a round hole, but somehow it works.
Well, not quite a square peg, but you've hit on the key point.
Okay.
CSpace, as it stands, is a type of Euclidean space where you can't have a perfectly closed sphere without causing a singularity.
Right.
However, the RCB gets around this by being diffeomorphic to Euclidean space.
Okay.
It's like taking a flat sheet of paper and cleverly folding it to create the illusion of a sphere.
So the RCB is kind of bending the rules a bit, finding a loophole to introduce a structure that should be possible.
Yeah.
But which might be the key to explaining how fermions exist.
Right. I wouldn't say sneaky, but definitely ingenious.
Okay.
And this idea of bending the rules actually has a strong precedent in physics. Remember symmetry breaking?
Right. Like that classic example of a perfectly round ball balanced precariously.
Yeah.
The slightest nudge and boom, it rolls in one direction.
Yeah.
Breaking the symmetry.
Exactly.
Yeah.
And the source proposes that this RCB is a form of symmetry breaking within CSpace itself. Maybe CSpace starts in a perfectly symmetrical state.
Yeah.
But the formation of these RCBs disrupts that symmetry, leading to the complex universe we see.
Now, that's a thought-provoking connection. It's like those RCBs are the cosmic dominoes that set off a chain reaction of complexity.
Right.
But this is all based on the big if.
Yeah.
If these RCBs can actually be created and observed.
Right.
The stakes are pretty high, right?
They are indeed.
Yeah.
If researchers can successfully create and study RCBs within these CSpace simulations, it would lend significant weight to this model of reality as a single unified substance.
Right.
But, and this is crucial, if those RCBs don't show up or they don't behave as predicted, It could throw a wrench in the whole CSpace concept.
Oh.
It would mean back to the drawing board, rethinking those fundamental assumptions about the very nature of reality.
Oh, talk about pressure.
Yeah.
So the source makes it clear finding these RCDs is like make or break for the whole model.
Right.
But let's assume for a minute they do find them.
Yeah.
What would that mean for our understanding of, well, everything?
It would be a paradigm shift, to say the least.
Yeah.
Think about it. A complete material description of reality.
Whoa.
No more separate laws for the quantum world versus the everyday world.
Right.
No more mysterious forces we can't quite explain.
Yeah.
Just this one substance, the CSpace, and its properties giving rise to the entire universe as we know it.
Okay. I'm getting chills just thinking about it.
Yeah.
But before we go full-blown science fiction here,
Okay.
I have to ask, the source mentions some serious challenges to actually finding and identifying these RCBs.
Right.
How big of a hurdle are we talking?
It's not going to be easy, that's for sure.
Yeah.
The first challenge is the complexity of simulating CSpace itself.
Right.
Remember, it's continuous, but they're working with a discrete model that introduces a level of approximation that's hard to avoid.
Kind of like those early video games where everything was made of blocky pixels.
Yeah.
Like you knew it was representing something real.
Right.
But it wasn't exactly high fidelity.
Exactly.
Yeah.
And this source emphasizes that numerical experiments, meaning simulations, should really come before trying to develop super complex mathematical descriptions.
Cool.
You need that data to guide you, to tell you if you're on the right track.
So it's a constant back and forth run, simulations, see what happens, tweak the model, rinse and repeat.
Precisely.
Okay.
It's like a massive scientific jigsaw puzzle, but you don't even have the picture on the box to help you.
Yikes. Sounds like a job for a supercomputer with a serious caffeine addiction.
Right.
But let's say they manage to accurately simulate CSpace.
Okay.
Then comes the problem of actually finding an RCB within that simulation, right?
Right, and that's no easy feat.
Yeah.
The source uses the term diffeomorphic to CSpace,
Okay.
meaning the RCB might blend in with the surrounding CSpace material. It's like trying to find a chameleon that's perfectly camouflaged.
So even if the RCB is there, it might be practically invisible.
Yeah.
How are they supposed to spot it?
Well, the source actually suggests enlisting artificial pattern recognizers, what we commonly call AI, to help with that task. AI is becoming a real game changer in science, especially for analyzing these massive data sets where the signal might be buried in a ton of noise.
Okay, so AI to the rescue.
Exactly.
Makes sense. They're great at finding those subtle patterns we might miss.
Yeah.
But I have to admit, this whole thing still feels a bit like searching for a needle in a cosmic haystack.
It does, doesn't it?
Yeah.
But even if this specific research project doesn't lead to that eureka moment, think of the knowledge and tools they're developing along the way.
Yeah.
It's pushing the boundaries of computation simulation and our understanding of the very nature of reality.
Good point. Sometimes the most valuable discoveries come from those unexpected detours.
Exactly.
But, you know, the source seems incredibly optimistic about this whole RCB concept. They even go so far as to say there seems to be no excuse for not doing the research.
Yeah, that really speaks to the potential they see here.
Yeah.
If this model is correct, it's not just an academic exercise.
Right.
It could revolutionize our understanding of the universe and our place within it.
Now, I know the source focuses heavily on the physics, but I'm curious about the philosophical implications, too.
Okay.
I mean, if reality is ultimately made of a single continuous material, what does that say about the boundaries we perceive between things? Are those boundaries even real?
You're right.
Or just illusions created by the way this substance interacts with itself?
Those are profound questions, and ones that physicists and philosophers will likely be grappling with for years to come if this CSpace model gains traction.
Well, because that's what happens when you start poking around at the very fabric of existence.
Yeah.
You're bound to uncover some existential questions along the way.
Absolutely, and that's what makes this research so captivating. It's not just about equations and data. It's about questioning the very nature of what we call real.
Okay, so we've established that finding these RCBs is mission critical for this whole CSpace model to work.
Right.
But let's dig a bit deeper into the Van table.
Okay.
The source mentions some really intriguing details about the internal structure of the RCB.
Yeah.
And how it's supposed to generate fermionic behavior. Are we ready to venture into those uncharted territories?
Let's do it. Remember how we were talking about the RCB mimicking the topology of a ball? Even though that shouldn't be possible in CSpace.
Right.
Well, the source actually goes even deeper.
Okay.
Describing the RCB structure as naturally structured as a donut within a ball.
Wait, a donut inside a ball?
I know.
That sounds more like a dessert than a fundamental particle.
I know. It's a wild image.
Yeah.
But the source explains that this seemingly bizarre configuration is actually homeomorphic with Euclidean 3 space.
Okay.
Meaning it can be smoothly transformed or untwisted into a simple 3D space. And this untwisting process is supposedly crucial to how the RCB generates those fermion-like properties.
Okay, so we're taking this complex, twisted shape and somehow smoothing it out.
Right.
But how does that relate to fermions?
Okay.
Specifically to their spin.
That's the million-dollar question.
Yeah.
So the RCB's complex topology, when smoothed out, can mimic the behavior of fermionic spin. This is crucial because spin is a fundamental characteristic of fermions,
right,
influencing how they interact with other particles and fields.
So the RCB itself doesn't actually spin in the traditional sense.
Right.
It's more like its structure and the way it interacts with CSpace creates this illusion of spin.
Precisely. It's a subtle but crucial distinction.
Okay.
And this is where those resonances we discussed earlier come back into play. The source proposes that the RCB's unique structure allows it to support specific types of resonances.
Yeah.
And those resonances are what ultimately give rise to the properties we associate with fermionic spin.
So let me see if I've got this straight.
Okay.
The RCB, with its donut in a ball structure, creates specific vibrations within CSpace. And those vibrations, those resonances, are what make it act like a fermion with spin.
You got it.
Oh.
It's mind-boggling. I know, but that's the beauty of exploring cutting-edge physics.
Well, I have to say, this whole CSpace model is one of the most mind-bending concepts we've ever dived into.
Yeah, for sure.
But I think we've done a pretty good job of unpacking it for our listeners today.
I agree. We've gone from the basic idea of CSpace as a unified material to this intricate dance of RCB's resonances and emergent fermionic behavior.
Right.
It's a testament to the incredible creativity and ingenuity of physicists trying to unravel the secrets of the universe.
And as we always emphasize here on the Deep Dive, it's not just about the answers. It's about asking the right questions, pushing the boundaries of our understanding, and embracing the mystery and wonder of it all.
Well said.
Who knows what other mind-blowing discoveries await us as we continue to explore the nature of reality.
Exactly. And that's the beauty of science.
Yeah.
There's always more to learn, more to discover, and more to be amazed by.
So to our listener out there, keep that curiosity burning bright and never stop exploring the infinite depths of knowledge. Until next time.